So in this video, I'm going to go over the gradient of a scalar function. So remember, our definition of a gradient is given by the nabla symbol over some function x, y, and z is defined to be the partial of phi with respect to x holding y and z constant, because x, y, and z are the independent variables. So here's our I, here's our j, which is the partial of phi with respect to y holding x and z constant, plus k, partial of phi with respect to z while holding x and y constant, meaning the independent variables are x, y, and z. Nobody wants to write y, z, x, z, and x, y constantly, so most textbooks, most authors just tell you that x, y, and z are independent. So we can actually reduce this writing just by removing the x and y, z, and so once we know they're independent, we don't have to waste time keep writing this over and over again. So we've done some examples already in calculating partial derivatives, but now what does this mean? So I'd like to explain what this really means. This is called the gradient of a scalar function. So remember, this is called the scalar function. Ooh. So this is the scalar function, and we're getting a vector. So we have something. We're plugging a scalar function into this operator, and we're getting back a vector. And so this corresponds to a vector field. So the scalar function is generating. So the scalar function is generating a vector field with the gradient operator. So what exactly is it doing? So that's the concept that I'd like to explain today. So to explain this idea, exactly what the scalar function is, right? What I'm going to do is I'm going to do a special case of an example of temperature. So assume that we're told the temperature. So this is the temperature at a point x, y, and z. So here's the temperature. So my problem now is, what is this vector field that's generated from this temperature, which is a scalar function? It has no direction, and we're applying it and plugging it into the gradient function. So this is the gradient, and we're calculating something. And so our problem is, what does this mean? Now to explain this idea, right? So imagine that I'm working in a two-dimensional surface, and that my temperatures, right, are actually on 2 dimensions, so we can understand it a little bit better. So imagine that at different points, right? So imagine that at different points we have something called an isotherm line. These are called isotherms. These are temperatures, isotherm lines, but actually surfaces. So isotherm lines are lines of same temperature. So for example, if I find on this surface, right, I'm only working 2 dimensions to explain this 3-dimension surface, but 2 dimensions, I find that along this line the temperature is, let's say, 100 degrees. And then at another point in the interior we get another isotherm line, and the temperature increases to 200. So along this line at every point, and somewhere in between there'd be like 150 degrees, but so this looks like an elevation map. So if somebody had to give you an elevation map, right, they'll take cross sections of different heights and say, this is the height 200 meters above sea level, this is 100 meters above sea level, and maybe, but I'm using temperature, so this is an isotherm line in 2 dimensions. So let's say this is at 50 degrees. So there is a 60 isotherm line, there's a 70, there's an 80, there's the 81, and so on, but they're all like layered. And let's assume that as we go to center, this is like 300, and finally at a point, right, there's 400 degrees. So right at the center is 400 degrees. So what I can say is that these isotherm lines, right, are basically lines where the temperature is a constant of 50, 60, 70, 80, 90, 100. And they create these different lines, closed lines. They might be open line going to infinity, but I'm just using closed lines example. And so now if you're working in three-dimensional space, right, these wouldn't be lines. These would not be called isothermal lines. These would be called, they'd be surfaces. So we have surfaces, right, where the temperature is uniform. For example, in this room, there's a heating element, right? Not a heating element, a radiator that's pumping out air, right? And I know that at different points in this room, right, the temperature, for example, temperature here, right, might be 100 degrees. I'm not 100 degrees, maybe it's let's make it at 25 Celsius, pretty warm. So it's 25 Celsius, next point is 25 Celsius, next point is 25 Celsius. But as I get closer to the heating element, right, it should be a little bit warmer. But I'm looking at these surfaces, right, that have the same temperature. So this is an isothermal line, but if it was in 3 dimensions, we'll call this an isothermal surface. So these isothermal surfaces, right, are basically surfaces that have the same temperature at every point along that surface. So for example, so I'm doing in 2 dimensions, but you have to imagine that, so for example, if this is a room, and for example, this is the door to the outside of the room, and here's the radiator, actually, so let's say it's a heating element, okay? So it's radiating heat. And I expect that the surface, right, probably like saying that closer to the room, let's say it's cold. And so the isothermal surface, right, might be like this, saying that around the doorway and on this room might be very cold. So it might be 10 degrees Celsius. But as you get closer to the warm area, to the radiator that's radiating heat in this area right here, it might be reaching a value of 25 degrees Celsius. 25 C, and somewhere in between those, right, there might be an area where it's these isothermal surfaces. So this might be actually 20 degrees Celsius, and another one might be close to between here, so 15 degrees Celsius. And so I can create these surfaces that are basically have the same temperature. And so here in 2 dimensions, isothermal lines, but if it's 3 dimensional, it'll be isothermal surfaces. So let's imagine that I'm going along one of these surfaces. So here is an isothermal surface. It's a surface, but I'm only looking at it 2 dimensions, so I'm cutting it and so on. So imagine that I have a position vector. Actually, let's listen. So here's phi. So or the temperature, right? Here's the temperature T. T is a function of x, y, and z. Now, if I'm traveling along that isothermal surface, right? So from this point, let's call it to another point. I'll call this difference, right, as dr, the change in the displacement. I went from here to here. And the question is, what is the change in the temperature going from here to here as I'm traveling along an isothermal surface? Well, you'd say, well, the change in the temperature between those 2 points, dt, between those 2 points, must be equal to 0 because I'm traveling along an isothermal surface. Because it's an isothermal surface, right, dt is equal to 0. Let's imagine that the distance from here to here is ds. Okay, so the distance, right, traveled from here to here is ds, and it's really the magnitude of the displacement vector, just the radial vector. So remember, whenever I do the radial vector, I'll always denote it by an r, and that really means nothing more than yj plus zk. So if I'm traveling along that isothermal surface, right, the change in the temperature must be equal to 0. But I also know from my basic understanding of multivariable calculus, right, that if somebody told you dt, and I'll do it in terms of ds so you can see it better. So this is the change in temperature with distance traveled. I've traveled from this point to this point, and I've traveled a small distance of ds. where s is the distance traveled, which is the magnitude of dr. So if I travel, right, I know from my chain rule from multivariable calculus, because t is a function of three variables, x, y, and z, I'm traveling along the surface. I'm not going in any arbitrary direction. I'm going along an isothermal surface. That's equal to the partial of t with respect to x times dx ds. So if you kind of remember, x, y, and z are independent. So this is your chain rule. So we know that if you're traveling along an isotherm, the change in the temperature with the distance traveled, right? Well, there is no change in temperature, so that's equal to 0. But I also know this. This is the chain rule. This is really the chain rule in multivariable calculus. So we've taken t as a derivative of x, y, and z. I'm sorry, as a function of x, y, and z. But if you look at it very carefully, this kind of looks very familiar. It actually looks like the I vector, I'll put a square bracket, j vector, dy plus k vector, tart t with respect to z, dotted with I dx ds plus j dy ds plus k dz ds. And if you think about this, this is actually, so this is the gradient of the scalar function, or in this case temperature, so I'll use t. And this is basically dr vector with respect to ds. So if you think about it, this is a unit vector that is traveling along the surface. So I'm traveling along the surface, and that's equal to 0. So what does this mean when you have two vectors, right? That dot products are equal to 0. And since I've traveled, dr is definitely, ds is definitely not 0. And when I calculate the gradient of a temperature, right? Temperature is a weird function x, y, z. I doubt very much that this is always going to be 0. So it's some non-zero value. So what does it mean when you have two vectors that are basically dot product? It means that the gradient of t is perpendicular to dr ds. And what does that mean? Well, what that means, right, is that if I'm traveling perpendicular to this gradient vector, I'm traveling along the surface, right, then the gradient vector must be perpendicular to that surface. So here's my isothermal surface. At this point, I might ask, what's the direction of it? All I know is that if I'm traveling parallel to the surface, then along this line, which is perpendicular to the surface, right, that's the direction of t. But I don't know if it's pointing in or out, but let's discuss this now. Exactly what happens when, so dr ds is a unit vector. If I dot it, right, with the gradient vector, we get 0. So this is perpendicular to my unit vector in that direction. But we can actually do it. What happens if, for example, that I ask myself, right, well, how is dt ds, right, changing if I travel perpendicular to this direction, in parallel to dt? Well, if I'm traveling parallel, then the dot product is cosine of 0, which means that, so let me erase this. So we know, all we know is that dt, so let's put some temperatures in here. So let's assume that this is the isotherm 100, and here's another isothermal surface, and this is 200. Okay? Let's imagine that I'm going in this direction towards the 100 to 200. Well, if I'm going in 100 to 200 direction, all I know is that, looking at this equation, so it's no longer 0 in this new path. So let me erase this. So let me erase this and put this in exactly. So here's dt ds. So the change in temperature with change in distance traveled. Now, as I'm going towards the higher temperature, right, dTTS is greater than 0 because I'm going in that direction. I'm increasing temperature. It's going to a higher temperature. The final temperature is 200, for example. It's increasing. And I'm traveling in that direction. So that means that, remember, this is really the magnitude of the gradient of T times the magnitude of dr ds. And this is 1. And this magnitude, right, times cosine of the angle between them. But what's the angle? Well, if I'm traveling perpendicular this way, right, and the directional directive is perpendicular, the angle between them is 0. So this becomes 1. And dt dr ds, right, it's a unit vector, so that's 1. So the magnitude is gradient of t is equal to dt ds, which is greater than 0. So to put it in other terms, right, what you're saying is that the gradient function, right, is basically a directional derivative that tells you the direction where temperature is increasing. So your gradient t, right, is basically pointing. You're pointing in the direction of increasing temperature. So from earlier analysis, we know it's perpendicular, but now we know what it really means. It's pointing in the direction of increasing temperature. So if this is 100 and this is 200, then that directional derivative means, right, this derivative, right, traveling along that line, the gradient of t means that it's increasing perpendicular and it's increasing towards the 200. So for example, if somebody gave you an isothermal surface like this, or isothermal lines in this case, and somebody drew another line like this, so let's say this is 100 and this is, let's say, 50. At this point it's 50 along the surface. So what is the direction? What is the gradient of this? We know it's perpendicular to the isothermal line, and what is it doing? It's always increasing towards the higher temperature. So in this case, at this point, right, it's always increasing towards the 100. So the isothermal line is going to be, so this arrow represents the gradient of temperature. And as a temperature is going to a higher temperature very quickly, then you find that the larger the value of the change rate in the temperature per unit distance traveled, if it's larger, you get a larger value in the gradient. So the gradient always points in the direction of increasing temperature for this temperature scalar field. So if I had a room and somebody drew some isothermal lines, so here's a room and it's a top view of some kind of a fireplace, so it's a top view of the fireplace. And we expect that there must be, I'm not assuming there's convection, so this is like assume that temperature does not change and that there's no convection currents and stuff. Let's not worry about things like that. So if I draw isothermal surfaces, right, maybe it's something like this, and this is closer to the fireplace, so maybe this is like 90 degrees Celsius. You'd get burned, but let's assume that this is 80, and somewhere over here this is 70, and so on. So if somebody asked you, right, what is the directional derivative, right, the gradient of the temperature scalar field at this point, you'd say, well, it's increasing this way, so the directional derivative is in that direction perpendicular is actually the gradient of t at that point. So what is the gradient of t at this point? It'll be going towards the increasing temperature. How about this point? This point, well, it's perpendicular to the surface line and it's going towards the increasing 80. So we're going. So we can actually draw these thermal lines, these gradient functions, right? So the gradient of a scalar field points in the direction of increasing values of the scalar function when crossing level surfaces. So these isothermal lines are sometimes referred to as level surfaces. In this case, it was level lines, but sometimes referred to as level surfaces. So hopefully you got a rough idea what it means to take the gradient of temperature field. So Now, once you know how to calculate what it means to have a gradient field, right? You have to do some calculations to make sure you can actually do some basic algebra and gradients. And so the next portion, right, is I want to go over some examples to make sure you know how to calculate the gradient. But these are rules. We can actually derive these rules, but it's too time consuming to go through all these details. So I'll actually tell you what they are. So for example, if you define the two scalar functions phi and let's say psi, the gradient, you can actually prove this step by step, which I won't go through, but you can review this yourself, and the derivations are not complicated. Just go to definitions. So phi and psi are basically scalar functions in x, y, and z. You'll find that that's equal to the gradient of phi plus the gradient of psi. So rule number one. Rule number two is that if you have a gradient times a constant times phi, where this is a constant, you take the gradient, the constant can come out of the gradient symbol. So we're trying to build up an algebra, right, so that we don't waste time wondering exactly what to do when you have some calculations to do. So here is the gradient of scalar phi. You have to get used to this because, especially in engineering, you'll be seeing a lot of these gradient symbols. If we're in physics, right, we tend to switch over to better notation than this, but it's a little more advanced than this. So either I teach you something like tensor calculus, right, and then going over index summation, or we do differential geometry and use D notation. But either of those is a little more advanced than this. So here is the gradient of phi, so a constant can be pulled out. You also, if somebody gives you the gradient of a product of two scalar functions, this is going to be it looks like you're taking a derivative in each of the individual elements. You can prove these statements really quickly, but I'm just not going to do it. It's just too much work. But there is one case that I really do need, and that's really because we need to do this for understanding central force problems. Okay, and so hopefully maybe I should give you some examples on this, right? So for example, if somebody says, what is the gradient of 3x squared y plus 7x squared z? You're going to say, well, it's basically the gradient of 3x squared y plus the gradient of 7x squared z. So if you have a constant, so if somebody asked you what is the gradient of 3x squared y, for example, right there, you're going to say, well, the 3 comes out, so this is the gradient of x squared y. And so hopefully you remember exactly what the gradient definition is and can do gradient calculations. So if somebody asked you what is the gradient of x squared z, you're going to say this is exactly the same thing as z, the gradient of x squared, plus the gradient of x squared z. Okay, you can actually prove these steps, but and I would highly recommend that you get a pen and paper, right, and spend some time deriving these things. Don't just look them up in a book. Spend some time deriving, because as scientists, right, you have to learn how to build ideas from scratch. Anyway, let's erase this and let's go to our next idea that I want to make sure you understand, because I need it for teaching central force problems. So remember, I said that, so actually let's just do it. So imagine that you're given a function f, and it's a function of r, the radial vector, where r, so actually let's use phi, because so here's a function of r, and this is where, so you're given phi is a function of r, so function, what is r? R is given by the square root of x squared plus y squared plus z squared, or if you're curious, the radial vector is given by xi plus yj plus zk. And the question is, what exactly happens if somebody asked you to evaluate phi at r? So we can go through definition. So remember, when I do this, I'm all implicitly assuming x, y, and z are independent. I keep reminding you because people seem to always make mistakes on this, and they get weird answers to things, and they're wondering, why did I get these weird answers? And so this is k. This is from definition of the gradient. So let me erase this since you know it's independent. But that's exactly the same thing by using the chain rule, right? I can take this and say, well, the partial of phi with respect to r is really the derivative of phi with respect to r times the partial of r with respect to x. Plus, because phi is a function of r, I'm using the chain rule. I put the total derivative so that you understand that this is really a partial of phi with respect to r, but it's only one variable, so I put a total derivative instead. So here is the partial of phi was really the total derivative of phi. So this is our chain rule, one variable. And here is d phi dr times the partial of r with respect to z. And we can pull it out. So we're now left with the the derivative of phi with respect to r, parentheses, of the I vector partial of r with respect to x plus j partial of r with respect to y plus k partial of r with respect to z. Okay, great. So next is, how do I calculate these values? So let's calculate partial of r with respect to x. So if you remember, r is given by this equation. So I'll do it in exponent form so you can see it better. So I'm taking the partial of x with respect to x squared plus y squared plus z squared to the 1/2. We're taking with respect to x. So in this case, right, we're pulling out the exponents, we do the Taylor's rule, you got 2x, so we get 1/2 of x squared plus y squared plus z squared to the minus 1/2 times the chain rule, right? So this is really 2x, so the 2's drops away, and we're left with x divisible by x squared plus y squared plus z squared. Now by symmetry, right, you can actually see that, so this is r with respect to x. So onto the calculation. We can also do the partial of r with respect to y, and by symmetry, right, you can see that whether I replace as x and y's, it's all symmetrical, right? So you'll get the same answer as y. And I'll actually write this in terms of x over r, because I already know what this is r, so I can write that. So this is y over r, and partial of r with respect to z is z over r. So let's continue. So what we've done so far, so I'll continue it over to here, right here. So let's put these in. So that's equal to the partial of phi with respect to r of I x over r plus j y over r plus k, and this is z over r. And if you think about it, right, what we're getting is this is a unit vector. Unit vector in the direction of r. So I can denote this by r hat. So what you're saying is that this is really d phi dr r hat. Now, this unit vector, right, is basically r over r. So I can put those in, and so we'll see that this is really d phi over dr times the radial vector divisible by the magnitude r. So we're left with 1 over r d phi dr r vector. And I want to keep it in this form. so you have an idea how to construct things. So let me give some examples of this, right, so that we know exactly what's happening. So basically, so let me summarize this. So our final rule is that, I'll write it over here just to make sure. I'm going to write it over again after I erase everything. So the gradient of phi, that is, has a function of r, which is the radial vector, right? And it's proportional to that. We find that that's really the derivative of phi with respect to r times r unit vector. And sometimes I'll write it like this, 1 over r. And the reason for this, right, is that I haven't discussed it yet, and we can apply the divergence, right, to these things, and it's easier to calculate divergence of r vector than it is to calculate divergence of r hat. R hat is a unit vector. Okay, great. So it seems like a lot of math, but it's not really. But the main thing you have to get out of this, right, is just know how to apply this rule. So let's go through the example of this. So if somebody gives you the gradient of, let's say, r squared, how do you calculate this? Well, I know that this is really the derivative of r squared dr times r hat. So it's not a dot product, it's r hat. So this is really 2r and r hat. But r hat, right, is sometimes written as 2r. R times r hat is r vector. So this is really 2 times xi plus yj plus zk. So let's be a little more, let's try another function. So for example, if somebody gave you a function like gm over r, what is that equal to? Well, you can take the derivative, so this is really the derivative, and I mean this to be the gravitational constant g, so gravity, 6.673 10 to the minus 11, mass is the mass of the object, so g is the gravitational constant, and mass is the mass of some object. R is the radial distance from the center. So if somebody gave you, what is the gradient of gm over r? The first thing you should do is, well, we know gm is a constant that will be pulled out, so gm comes out. And the gradient, I'm now calculating, of r minus 1. But that's equal to gm, take the derivative, or r minus 1, with respect to dr. So we get minus 1 minus r to the minus, gm r to the minus 2. Okay, so this is actually minus gm over r squared. So at this point, right, let me go into exactly why I need the gradient of these radial functions. So let me erase everything. So that's an example of you calculating gravitational surface radial. So our whole problem, right, and the reason we have to go through this is that we have to understand exactly. So imagine the following problem. We have a satellite. Well, not a satellite, just here's the Earth. And there's a satellite going around a circle, and all I know, right, is that this force of gravity on this small little satellite, right, the force of gravity. So if you think about it, so the radial vector, I'll assume the Earth is at the center of my coordinate system. Here is my r vector, which is xi plus yj plus zk. I'll always do r for the radial vector. So here's my radial vector, force of gravity. What is the direction of force of gravity? Force of gravity is towards the Earth. And by Newton's law, it says that if this mass of the Earth is m, and the mass of the satellite is lowercase m, then I expect, right, that the mass, the Newton's law basically says that the force between those two particles, right, is gmm over r squared, the distance between them, and the direction, right, happens to be minus the unit vector in the opposite direction. And the question is, looking at this force of gravity, right, is gravity a conservative field? Is gravity conservative, simply put? Now, the force of gravity in this particle is gravitational constant times the mass of the Earth times the mass of the satellite over r squared over r hat. Is gravity conservative? Well, if it's conservative from our definition that I've used in lecture, right, it said that there must be some kind of a potential function v, so this is true. But we already know how to calculate things, because if somebody gave you a potential function in terms of r, I know how to calculate this. I know that this is equal to the derivative of v with respect to r hat. But guess what? This would mean that, so we already know the gradient of any function that's a function of the radial distance is given by dv over dr. The minus carries with it. And if we equate both sides together, we'll actually see that, so we're saying is minus g, I'll write this again, mass of the Earth, mass of the satellite over r squared is equal to minus dv dr. And actually, maybe I should put the or hats in just to make sure you understand. So these two vectors are equal, so this must mean that gm m over r squared is equal to dv dr. And so the question is, can I find the v? And if you think simply put, right, v is nothing more than the antiderivative of gm over m, mass of the Earth, over r squared dr. So once I can find this value of v, then I know that gravity is a conservative field. And if it's conservative, it means that if I deal with forces and velocities and kinetic energies, right, they're conserved. Energy is conserved in a conservative field. Kinetic energy plus potential energy is conserved. So that was the point. So let's calculate gm over r squared. So if you remember, I'm doing these steps to make sure you understand slow detail. So this is really gm lowercase m integral of r to the minus 2 dr. So we increase this by 1 and divide, and so we're left with gm m with a minus, because we're divided by minus 1, and over r, plus a constant. So our potential, right, is given by v at r is equal to negative of gm m over r. And this is a starting point. So if we have a gravitational central force, so let me summarize this. So if we have a central force of minus gm over r squared, then the potential associated force of gravity is equal to the gradient of v, where v at r is given by minus g m m over r plus a constant. So that is the actual scalar function associated with the conservative force of gravity. So this is the vector potential, or sorry, not the vector potential, I'm sorry, the gravitational potential energy, right, associated, or the potential, right, associated with the force field, minus gmm over r squared. Okay, great. Now what does this have to do with anything? And the reality is that now we can actually do the equations of motion for objects in a gravitational field. So the question is, what is the motion of this object that's traveling through space? And I'll leave that for another video, but basically we're going to plug these into Lagrange Euler equations of motion, and then we get ourselves the equations of motion for particles traveling around a central force, gravitational field, like the Earth. And so once we have those equations, right, then we can solve those equations and we should be able to say what the trajectories of these satellites are. And we're actually going to generally see that these trajectories are going to be elliptical, spherical, circular, elliptical, parabolic, hyperbolic, and so we're going to get these standard equations of these particles of a satellite traveling around the Earth. Anyway, so let me summarize everything that I've said. It's quite a lot, actually. So I wanted to make sure first that you understood the idea of what gradient means. So the gradient of a scalar function, right, is basically it's a direction it points in increasing phi. So if you have a level surface of phi, then the next level surface, whichever direction increases phi, that's what the direction is. It's perpendicular to the level surface and it points in the direction of increasing phi. We also gave you some algebra, right, manipulating the gradient function. So I gave you rules for manipulating. And we also looked at a specific case of if somebody gives you a function of r, we know that the gradient of a radial function, right, r, is given by nothing more than the derivative of r with r hat. And actually I did also show you that if somebody gave you a force of gravity and it's minus gm over m over r squared, r hat is the force of gravity, we can actually write it in terms of the negative of a gradient potential function. We'll call it v. And v happens to be minus gm m over r plus a constant. But that constant will disappear when I plug it into the equations of motion for Lagrange. So we did a lot, and hopefully it's a long video.